And now we're going to hear what I think is probably one of the most interesting aspects from the study. And this is water quantity and how water quantity stream flow changes with forest management, especially timber harvest. And in the other panels, we've done science, management, water. This one is science and science. So you get a double dose of science. And first we'll have Kevin Bladen, who you've already met today, but I'll just refresh for you that Kevin is Associate Professor of Forest Hydrology in the Firm Department. And Kevin is really an expert on forest management and water. And one of the exciting things I just saw in a press release from OSU is they're reinvigorating part of the Hinkle Creek Watershed study to look at post-fire from the Archie Creek. And of course, who would be leading that but Kevin Bladen. So Kevin, tell us about water quantity. Looks perfect.
Okay, great. Thank you, Mike. Keep track of the time here. And I've underlined the short summary, just like with the sediment piece. For this review, we looked at about, I don't know, a couple hundred papers and whittled this down to about 100 of those that are relevant to Oregon. And so what I'm going to do in the time that I have available is really just show you a few of the results from some of the key pieces, I think, that really do a nice job of highlighting the overall findings. But certainly if you want more info, you're going to have to dig deeper into those pieces that are in this review. Again, given the broad range of backgrounds in the audience here, I also thought it would take a little bit of time very quickly at the front end to just think about, well, why do we care about stream flow? And you may have your own ideas, but there may be some things in here that you haven't thought about. I think for probably almost all of us this morning, when you turned on the tap for the drink of water or the shower, you may not have explicitly thought about, hey, where is this water coming from? But we know, those that have tracked it, where water originates, 2/3 to 3/4 of our water supply here in Oregon originates in our forests. So critically important in terms of a downstream drinking water supply, irrigation supply. And as a result, those folks that manage water in dams, thinking about how much water do we hold back? When do we hold it back? How much do we release for in-stream flow needs? I think those folks really need good information on stream flow and how different disturbances might influence that water supply. Similarly, a lot of our infrastructure downstream is engineered based on historical flows. So if we get changes in that flow regime, that can have really costly consequences. Certainly there's implications for water quality on a couple different fronts. We get elevated flows that can increase erosion, and movement of sediment through our systems. And along with sediment often comes things like phosphorus, which is adsorbed to the face of that sediment, or heavy metals. Higher flows can move more soluble nutrients like nitrogen, for example, as well. And then the flip side of that is, well, if we get lower flows, that can lead to increases in concentrations of nutrients, increases in temperature, and really all of these things have implications for aquatic ecosystem health, as well as some of those values that we take from healthy water supplies and recreational values. So lots of reasons to be concerned and think about impacts on stream flow. And so because of that, really not surprising when you look back in our history, we have been studying disturbance effects on stream flow for over 100 years. There's more than 250 papers in the literature that have explicitly dealt with this from around the world. These are results from one such paper, is from 1996, where John Stednick took all of the results for the contiguous US and put those together in this form, where we had percent harvested on the x-axis and the annual water yield increase change on the y-axis. And for today's discussion, I've highlighted these orange ones here, which are the Oregon studies that were in this review paper. And so I think this is a really good place for people to start if you're unfamiliar with this literature. And not surprising, like we've seen with lots of these studies, lots of variability, right? Look at 100% of a watershed harvested. We go from 0 response all the way up to an annual water yield increase of almost 750 millimeters. In Oregon, we have order of magnitude difference as well. So lots of variability tied up with catchment physiography, tree species, climate, the approaches that we take to harvesting. And so this is not a simple relationship by any means. Similar to what we talked about too, if you go back in time and look at a study like this, important to think about what's in it and what is it summarizing. And again, a lot of these are older practices that are no longer used. And unfortunately, we really haven't kept pace in terms of our research investments like we had in the 70s and 80s. And that's unfortunate, because I think there's been some really dramatic changes in our regulations and practices in recent years, and we're sort of missing out on some of that important story. So a couple pieces to get into and talk about today. This is the type of study I wish we had more of. Here this is the Mica Creek study in Idaho, and why I wish we had more of these. This gets to the scaling thing that we've been talking about quite a bit today, especially with thinking about communities downstream. And so these folks had several upstream watersheds they monitored, and then they monitored those downstream for several years. The way that they approach this is just ideal as well. They have a calibration period for 7 years where or 6 years where they monitor all these watersheds to develop relationships. Then they inserted the roads and looked at the roads by themselves for just 4 years. And then they harvested the watersheds and monitored those for another 4 years. What these figures here show, on the x-axis is the reference watershed, y-axis being the harvested watershed. The squares are the calibration periods. There's a bump up in all of these as we go to the circles as they put in the roads, and then the inverted triangles here with the harvest and roads. Okay, for orientation, I've also put here the percent of catchment harvested. So we're going from 48% to 24% to 18% down to 9% of the catchment harvested. And these numbers I've included here are the percent change in annual water yield. So here in this case, almost 50% of the catchment harvested. You add roads and we get a 12% increase in water yield. You add harvesting and we get a 36% increase in water yield. Interestingly, as we move through this, and a smaller proportion of the watershed harvested, a smaller increase in annual water yield. And this is where this study is really important, that they looked at this at this larger scale here. You've got this entire watershed number 6 here unharvested, which is the x-axis down here, and C7, which is this place right here. So you've got the harvesting in the upstream, which causes a 36 to 23% change in annual water yield. But as you move downstream, that signal really becomes washed out by the other contributions from the watershed. So a key piece there. Moving a little further north, the Upper Penticton Creek study. This study consists of a couple of watersheds, are about 1,100 to 1,200 acres in size. These are really consistent with Pacific Northwest, high elevation, snow-dominated catchments. This upper figure shows the 7-year pre-harvest weekly water yield. So the blue line is our reference watershed here, tracking ever so slightly below the watershed that was to be harvested. These are pretty good pair in terms of a watershed study, but that harvested watershed had just a slightly higher spring freshet in the pre-harvest period. As we move to the post-harvest period, and you roll this all together like they did at Mica Creek, there was about a 5% increase in annual water yield. But what's really cool about this study is actually that they broke it out and looked at it in terms of a weekly water yield. And when we do that, some really interesting nuances pop out and shifts in timing of that water in the streams. And in fact, when we look at the spring melt in these watersheds, we saw 20 to 30% increases in stream flow. And as we move into June, July, that results in about 17 to 23% decrease in flow. And so a lot of this has to do, again, high elevation watersheds. You've got an increase in accumulation of snow water, more radiation on those that increase the timing of melt. And something the authors noted, which was really important, they noted it multiple times that, hey, while we see this, it doesn't necessarily mean we're going to see this everywhere. What's unique about this watershed here is that it has very coarse soil content and has very low water holding capacity. And so certainly in watersheds that have similar characteristics, we may observe very similar things. But certainly this is an interesting finding and something important for thinking about water managers, in-stream flow needs for aquatic ecosystem health. So annual water yields, yeah, great. That's interesting and important overall for managing water. I think the things that many of us are concerned about and think about, though, are peak flows. To be honest, peak flows is probably one of the most contentious issues in the hydrology field. It has been for a lot of years. I've seen a lot of finger pointing and people getting, high blood pressure and pointing fingers at each other over this. It's complicated. Part of the complication, think about peak flows, 1 in 50 year, 1 in 100 year event. How many of those do we truly have in our data records? Very few, right? So we're working with limited data sets, even where we may have instrumentation in place to actually measure it. It's often blown out and we lose that data. And then on top of that, because we're working with smaller data sets, we get into squabbles about how we analyze that data. So this is really complicated. Regardless, we have the data that we do have. We have been able to discern that yes, certain practices can lead to increased probability of peak flows. We've heard about roads, density, connectivity. The more dense roads we have, the more connected we have, the greater probability of peak flows. And of lesser importance than the roads, but still very important, are how efficient our catchments are at draining water, both the hill slopes themselves and in the streams, our clear-cut sizes and buffers. And so it really depends on how all these things come together to influence peak flows, and why that's going to, by itself, is going to create variability. Gordon Grant, who did a really nice review recently, also noted how hydro regions come into play, and that we have different responses whether we're in rain-dominated, transient snow zones, snow-dominated regions, and it really depends on how those regions, how the processes, the hydrologic processes that are affected by our activities change peak flows. And so here, the snow dominated zone in the white, the light gray are the transient snow zone, and the dark gray, the rain zone. And we could see that, yeah, in the rain and transient, transpiration or tree water use is critically important for peak flows, but less so in the snow zone, where it's far more important in terms of how we influence snow accumulation and melt. And so all of these things coming together really complicate this problem. So this is a summary. This is in the chapter, and all of the papers associated with it are linked. This is a summary of all of the research in the recent years on how the percent harvested on the x-axis changes peak flows, and broken out by rain zone, transient snow zone, and snow zone. We've also got it broken out by the different treatment types. Is it a clear cut or a patch cut or a shelter wood? Are there roads in these systems? And so trying to summarize all this very briefly, the major findings, yeah, as we increase area harvested, that's where we're seeing our greatest peak flows. It's not simple though. You can see these gray bars are really standard errors where we see no change, statistically no change associated with harvesting. So we have instances in all of these systems where we have measured and quantified no change in peak flows with close to 100% area harvested. Similarly, there's not a consistent pattern in here related to treatment type. So in other words, you know, are clear cuts causing more peak flows than shelter woods or patch cuts? There's no discernible statistical pattern there. And what's not really illustrated here, but is buried in this, is that the greatest changes we see are for those more frequent peak flow events. The one in 1 year, 1 and 2 year events, those are modified more greatly. Those less frequent peak flow events, the big 1 in 100 year event, really we don't see evidence of that being modified by our forest practices. Again, that's with a grain of salt, because we have very few observations at this upper level, but what we do have, that's what the results illustrate. So in terms of today, you know, we were thinking about drinking water supply and implications downstream. This was something that the grant paper did address directly, and they hypothesized that peak flows in headwater catchments likely diminish downstream. The reasons they gave for that was that as you move downstream, you probably have increased opportunities for floodplain storage, that we have hyporheic exchange and opportunities for storage in the stream bed. The channel itself confers some resistance and can slow flows as you take up some of that energy as you move downstream. Similarly, as you move downstream, we tend to have lower slopes in our channel, which are going to slow the flow. And importantly, you know, as we saw with the Mica Creek study, while it was annual water yields, they relate the same thing, that as we move downstream, the proportion of area disturbed generally decreases, right? And there's less likelihood that we see some synchronicity of all of our subcatchments coming together to create large peak flows downstream. Again, with all of this, there's uncertainty. What you're seeing off to the right is one study from northern British Columbia. This is now where it extends in very high north, very strongly snow-dominated watersheds. Difficult to push that around and say, well, is it relevant to here? But it is an example that shows going from a reference period to a disturbed period at a large basin scale, now 600 square miles, we see increased occurrence in peak flows. The problem is, as we've talked about, as you go to a larger scale, it gets more complicated. These folks tried to break it out just simply by going, okay, how much of this is coming from pine beetle versus harvesting versus fire? They ignored our human footprint completely in this, and they were still unable to really disentangle this and attribute these increases in peak flows to a single disturbance. Like I say, it's complicated moving downstream. So moving out of peak flows, and the opposite of that is summer low flows. This is something that has been on a lot of folks' radars in recent years. A lot of that came forward with this Perry and Jones paper. It's a really nice paper, and I think what it speaks to me is the importance of investments in long-term data. We have these stories historically because our data sets haven't been long enough. This required a 60-year data set to elucidate these trends. And so what they showed here, what's being showed here on the x-axis is years after harvest. On the y-axis is the percent difference in stream flow in the summer low flow period. So July, August, September, each one of these lines represents a pair of catchments and their relationship to each other, a harvested watershed and a reference watershed. Not surprising based on everything we've talked about. This gray band here is sort of our expectation of what we would expect to see in terms of annual water yields. Anything above this is an increase in flow. We got more water in the stream than we'd expect. Below this, less water in the stream. And so, you know, in those first few years, we've got more water in the stream in most of our catchments. But as we transition and move down here 15 plus years, we end up in all of these watersheds with less water in the summer period than we would expect. Okay, so the questions are always, well, why is that happening? And so what these authors attribute that to is differences in tree physiology between younger stands and older stands. And we have some research we can rely on. This is some work by Georgianne Moore from the H.J. Andrews. And what Georgianne Moore and others showed was that the mean daily sap flux density, all that is how much sap flow per unit sapwood area there is. That mean daily sap flux density was about two times greater in younger trees than older trees. And also when we look at a stand scale, there tends to be more sapwood area overall. And what that leads to is tree water use that may be about 3 times greater in those younger stands, up here, versus those older stands. And there's a great paper by Dan Moore out there, and Dan sort of puts a lot of this together. And he hypothesizes, yeah, this is part of the equation, but there's other factors in terms of the process that we need to look at and think about that might be contributing to this. So that's one study. The questions become, do we see this sort of thing elsewhere? Again, fortunately, going back to the Alsea watershed study, we have a long-term record. We have data that goes back to the 1960s across these 3 watersheds. These get re-instrumented in 2006, some 40 years later, and allows us to look back and compare with the pre-harvest period. There's more to this story, which is really interesting, but we don't have time to talk about today in terms of flows and sort of the impacts of harvesting. But really for what we're talking about, we're going to focus on this period and the summer low flow period. And so what we found, this is a study led by my colleague Catalina Segura, and a really nice piece of work by her. And so what this is showing, the figure here, is similar to the Perry and Jones. We used a similar approach so we could compare and relate these studies. These gray bands are what we would expect in terms of flows across the X's, the different months and times of the year. This red line is needle branch, the one that had the greatest footprint of harvest, and so has the greatest footprint of younger trees that may have that higher level of transpiration. And so we did see declines in stream flow in that period, 40 to 50 years after the harvest, of about 25% over the entire year. When we just isolate the summer low flow period, that drops to about 50% of what we would expect based on that pre-harvest period. So putting all these together, how did the Alsea compare? There's a figure in that paper that compares the Alsea study with those studies from the H.J. Andrews and Coyote Ck, and really found that at the Alsea study, those were more persistent and deeper declines than what were observed elsewhere. Again, has to do with differences perhaps in rain dominated versus some snow, transient snow, differences in radiation loading and transpiration rates in these catchments. Okay, just keeping an eye on the time here. I think I have a couple of minutes left. So those are 2 studies. There have been lots of studies that have started to come elsewhere. This is one from British Columbia. You can see the pre-harvest period, the harvest period, and then in the immediate post-harvest, I think it's about 15 years after, we see elevated flows, which decline and become deficits for about 19 years. In Upper Penticton Creek, the pre-harvest period and compared to the post-harvest period, we also see evidence of this, 11 to 68% declines in summer low flows. They see the same thing at Mica Creek, elevated flows in the immediate period, and those drop 25 to 30 years out. And Dan Moore and I from UBC, Dan from UBC up in British Columbia and I have sort of gathered up all these data sets and are planning a reanalysis of all of these with the same metrics. Let's put them all in the same playing field to see how do they compare and are we seeing similar things. So this is from some forthcoming work, but wanted to show this site because it's unique compared to the others. It's a rain-dominated coastal redwood site in Casper Creek. And whether we're looking at 1-day flows, 7-day flows, 30, 60-day flows, summer yields, or low flow days, we're seeing evidence of this persist. Okay, so my very last thing I'm gonna throw in while I have 40 seconds by my clock, Mike, is many of you don't know me as a scientist researcher, but my main area of research for the past 17 years has been wildfire effects on water quantity, quality, aquatic ecosystem health, drinking water treatment. And so not surprisingly, I've been extremely busy over the last little while, but thinking about what we just talked about, and the scale and scope of these fires, Beachy Creek, Lions Head, Holiday Farm, Riverside, the Archie Creek fire, I have all kinds of questions about the implications for water yields and peak flows and long-term low flows as we have dramatic flips in our, at the basin scale. I think we don't want to miss that opportunity to capture that data. And so I'll leave it there. Thank you.
Excellent. Thank you, Kevin. I think this is going to be a whole nother phase of your research and maybe a whole nother conference coming up in a couple of years. So at this time, I want to introduce phase 2 of the science. Dr. Shrajita Basu is a water scientist with Sustainable Northwest, and she works across the forest and the water programs at SNW, focusing on collecting and analyzing data in order to protect the water quantity and quality in different watersheds. And she's done some really interesting work here. So welcome, Srijita.
Hi, everyone. Thank you, Mike, for the introduction. And I just want to check before I start that you can hear me okay and you can see my presentation.
We can hear you great. You need to start the presentation. We just see the overall thing, yeah.
Great. Yeah,
Perfect.
Thank you for that. Also, thanks to Kevin for setting the stage for the water quantity panel. So the topic of my presentation today is on the Oregon Coast Community Forest Initiative and my work on some of the VELMA modeling on Arch Cape. And I am working as a water scientist with an organization called Sustainable Northwest, which is natural resource nonprofit based out of Portland. So just to give you a quick overview of the outline of my presentation today is I'll be talking about the background on how this work started on the coast, and then touch a bit on the Arch Cape Water District, the work we've been doing on the financial and hydrological modeling, and then see how all these pieces fit together in terms of funding and implementation and acquisition of the drinking water source area. And then conclude with the summary of findings and some of the next steps following this research. So just a quick slide about Sustainable Northwest. Our mission is to protect natural resources and to look for collaborative solutions that work for people and nature. So some of the motivation for this work stems from, I've used 2 quotes from the Trees to Tap study and an existing DQ report from 2015 is how lucky we are, to live in Oregon and to be blessed with these beautiful forests that serve as drinking watersheds for our coastal communities. And while these coastal communities are very vulnerable to climate change impacts and other geological setting, the main concern is, a lot of these coastal watersheds are owned by private timber owners, and some of the times these communities do not have the chance to interact with these stakeholders and talk about decision-making processes about how their watershed would be managed now and in the future. So to fill in that gap of technical assistance and capacity, Sustainable Northwest bridges this gap in terms of launching the Oregon Coast Community Forest Initiative, which started in 2015 to bring together different partners and stakeholders, including private landowners and land trusts for acquisition and municipal water leaders, to look for collaborative opportunities on certain public drinking water systems, for example, Archcape, that rely on surface water, and then look for, where on the Oregon coast would a community forest approach deliver both economic and ecological benefits to local stakeholders. And on the left, you see a map done by EcoTrust, part of our phase 1 mapping effort to look at vulnerable drinking water source areas on the coast that have been impacted by forest cover changes in the past. And there's an excellent story map that I can share later. So without further ado, just a quick 30,000 foot level for folks who do not know what community forests are. Community forests are working forests owned and managed by either a local government or a community-based organization on behalf of a community, and have these following characteristics. And it's a popular model that's been adapted in New England and other places like British Columbia. And until recently, several places in the Pacific Northwest have adapted community forest models like Nisqually and Butte Falls, and there are other examples. So this is a map showing the project that I'll be talking about today that we've been helping with some financial modeling and hydrological modeling with. So this is Archcape, just south of Cannon Beach. And it is a drinking water source area that is fed by two creeks, Shark Creek and Asbury Creek. And it's about, the triangle that you see on the map is about 1,250 acres, but the orange piece that you see is the Archcape Community Forest Project, which is in line for 2,100 acres fee title acquisition that we've been involved with in the last 2 years. So we've been working closely, and I've been helping the committee with some of the hydrological modeling that I'll be talking about in detail. So this is excellent drone footage of the Archcape Community Forest. You see the green parcels highlighted there are the fee title acquisition, and the red parcel on top is a project of the larger rainforest acquisition project led by North Coast Land Conservancy. So in order to understand the watershed condition and how forest management practices could or would impact it now or in the future, it is important to rely to landscape-based decision-making hydrological models. And one such model that I have been applying and learned about is VELMA, which stands for Visualizing Ecosystem Land Assessments. So it is important, if a community owns the forest in the future, how would it manage it as a working forest? And what are the different trade-offs to look for alternative forest management scenarios? Would it have wider riparian buffers or some retention harvest practices? So it's really to find a sweet spot in terms of having higher ecological flows for fish habitat. A lot of these drinking water source areas on the coast have habitat for salmon, which is so important. And also these drinking water source areas rely on municipal drinking water. So it is important to see what's the sweet spot in terms of all these attributes. So to touch a little bit, I know I don't have a lot of time, but I'll try to be short and give you a big overview of what VELMA is and how it kind of functions and works. So VELMA is an eco-hydrological model, and the data generated from models like VELMA can help inform the future implementation of a forest management plan. So it can help identify locations in the watershed that could be most vulnerable to forest cover changes, for example, or climate change or fire, and quantify these benefits. So it's a model that depends, and each pixel is defined by a 30-meter pixel, which is divided into a 4-layer soil column. There are different drivers and inputs required to run these models, like, for example, the total precipitation data, and then what are the soil texture and porosity values. It's been calibrated on a lot of other factors that are listed on the left, and which could tell you what are some of the drivers that impact these changes in the stream flow, either in the total stream flow or the seasonal flows that I'll be talking about in detail. So going to my next slide. The hydrological model in VELMA is also linked to a plant soil model, which is a biogeochemical model. So the hydrological model and the biogeochemical model interact across multiple scales. So the main question is, how do you kind of translate from a small plot scale level to a large catchment scale or basin scale to see this impact? And this is when models like VELMA can come in and tell you about the interactions and processes on these bigger scales. So VELMA helps us to understand all of these interactions across a bigger regional watershed scale. Some of the applications of VELMA has been recently for salmon recovery planning on the coast, which ODF&W is leading, and it's been applied to the Nisqually Community Forest, a lot of stormwater management studies out of the urban area in Seattle, and recently for wildland fire effects on water quantity. So coming to the Archcave watershed analysis and how I've assimilated all the spatial data layers. So this is a diagram showing what all goes into the eco-hydrological model VELMA to tell you the results. So for example, on the left, you see the forest cover and age data. So I've divided the Archcave watershed in terms of the conifer and alder species from the lemma data that I got from OSU. And then I've also calibrated it based on the existing soil texture from the STATSCO and SERGO data layer. And the temperature and precipitation piece, which is very important, comes from the PRISM database. And this is all from the historical climate data, and the climate is constant in the scenarios that I'll be talking about. So I haven't used climate change models to see the impact. So climate is from the historical observed climate data. But what I have seen is I've changed other drivers related to forest management to see how disturbance impacts stream flow. And all this is based on the topography and hill slope that comes from the DEM taken from the NLCD database. So all of this goes into the model, and we can craft different scenarios. For example, a baseline scenario, and then a what-if management scenario, what you want to look at. And I'll be talking about that in my next slide. So it is important, because I did not have continuous stream flow gauge data from Archcave's drinking water source area. In order to test the confidence of the results and the calibration of the model, I had to rely on a long-term USGS gauge data out of the Nehalem Basin, which is the same ecoregion of the North Coast. So comparing the model flow with the observed flow and precipitation, I got a Nash Cliff coefficient of 0.876, which is higher than 0.7 and gives good confidence between the observed and simulated flow results. So talking in detail about how I simulated these disturbances in the Arch Cape watershed, I just wanted to be clear that these are all hypothetical scenarios, and this does not imply any information on how the watershed was managed in the past or what is occurring now in the present. So these are just scenarios to compare and do research on to come with some data and metrics on the impacts that could occur if we manage it in a certain way. So these scenarios on the left that I have compared is the baseline scenario, which is the natural succession, where no harvest or management would occur, and the landscape would just keep growing with forest age and cover. And then on the right are two scenarios with a 40-year rotation, even-aged, clear cuts. And then on the right, on the extreme right, you see is a 80-year rotation. So the same places the clear cuts would happen, but on a longer rotation, which is 80 year. So just touching a little bit on how the forest age was looking at the beginning of the simulation in 2012, mostly about 40 to 45 years when I started the simulation runs, and how I structured the simulation was doing the harvest in 10 years for about 50% of the drinking water source area would get cut. So just replicating some of the harvest done in the past and future forwarding it into the future, and then comparing these scenarios to see how it would impact specifically on summer low flows and spring flows. I have not included the peak flow results, but I do have them if anyone wants to look at those or have questions. I know the time is limited, so we can touch base on that later. So this graph shows the total annual water yield that comes from both the surface and subsurface flows. And the red line shows the disturbance occurs in both the scenarios, which is in the 40-year rotation, which is shorter rotation. And the yellow line is additional disturbance that occurs in the 40-year. So in the beginning, when the first disturbance is simulated both in the 80-year, 40-year rotation, you see the response is quite similar when compared to the baseline, which is the blue line, and the green line is 80-year. But once the disturbance occurs, there's a increase in the peak flows for about 4 to 5 years, and then it drops back to match with baseline. And then here, when the yellow disturbance occurs for the 40-year scenario and not for the 80 years, the 80-year runoff almost matches to the baseline scenario. And you see the runoff increase is only for the 40-year scenario compared to the 80-year longer rotation. So because these flows are summed up in terms of both the lateral and surface and subsurface flow, so it is difficult to see the changes, but in my coming slides, when I see the seasonal flows, it will become more clear. So looking at this figure, which on the top is for 80-year rotation for almost 93 years of simulation run, starting from 2012 to 2104. I have on the y-axis, you see a similar way to look at the data in Perry and Jones' paper, if you read it, is to compare the difference of the treated parcels with the baseline scenario when there is no harvest. And you see that both when you compare the 80-year rotation on top and 40-year rotation at the bottom, the places where disturbance occurs, there is an immediate response to increase in stream flow, which stays for about 4 to 5 years before it hits deficit. So our baseline is at 0. And then if you see, compare April and May legends, the spring flows increase for longer rotation for about 15% when compared to baseline in April and May. In the bottom figure, you see 40-year rotation. After 2 disturbances, the summer flow, the spring flow deficit is quite significant as it drops down the baseline condition as compared to the 80-year rotation. Coming to the change in average daily flows for the summer low flows. So for the summer low flows, after 2 disturbances in the 40-year rotation, you see that it ends up quite low, almost to 50% as compared to 80-year rotation, which stays around at 30%. So summer low flows are lower for about 20% in a 40-year rotation compared to an 80-year. And like I said before, these summer low flows also increase for about 4 to 5 years before a significant drop in the summer low flows occurs relative to the baseline condition when there is no harvest. So some of this research has been seen also by Perry and Jones and Segura et al. In 2020, looking at younger forests of Douglas fir stands taking up almost 3 times more water, especially in the summertime, compared to mature stands. And this is all related to the leaf area index and the basal, the sap flow basal area, which is higher when younger forests are like straws are sucking up more water as compared to longer and more mature stands. So I just want to show you the changes in the evapotranspiration. So from 2059 to 2093, I see that the baseline condition uses much more daily, much less daily evapotranspiration, much less water as compared to the 40-year or 80-year rotation, which is somewhat similar to the published research out of the Nisqually Community Forest, where summer low flows for younger forest stands was almost triple less than the mature community forest longer rotation scenario. And then comparing the total average daily biomass, you see that for the baseline, it is the highest, which is almost 35,000 gram carbon per meter square when compared to an average biomass pool. So when I say an average biomass pool, it sums the biomass pool from the above ground stem, the root, and the leaf. So it kind of clubs into a biomass pool into VELMA. And it is significantly lower for 40-year rotation, which you see over time when you compare it to an 80-year rotation, which is the green lines here. So some of the key takeaways from this preliminary work is surface runoff does increase in the watershed, and that is seen just right after harvest, which sticks around for 4 to 5 years. And after a disturbance, this occurs is because forest cover decreases the direct interception, and there is potential to increase soil moisture levels, thereby increasing peak flows. I've not included the figures for peak flows because I just wanted to concentrate on summer low flows, but I can definitely get back with those values. And summer low flows are highest in the baseline scenario and decrease significantly for shorter rotation as compared to a longer rotation. And this impact in the late summer flow is seen after about 50% area is harvested in 10 years. So I've also seen this impact kind of die down when the harvest area was almost between 20 to 25% in the 10 years time. So it definitely is sensitive. The results are sensitive to where the harvest occurs in terms of location to the stream channel, or how much of it is harvested in a short period of time. So, daily evapotranspiration in baseline is lower, so it uses much less water as compared to shorter or longer rotation scenarios. So, I guess I have almost 5 minutes to wrap up. I'm sorry, 2 minutes to wrap up. So I'll just quickly say that, the objectives set by these scenarios would be finalized in a working group from the Arch Cape Water District Board, composed of area forester, to see which scenario we would be finalizing in terms of having some retention harvest or wider riparian buffers, and then we would compare that and include those results into VELMA. So in terms of where VELMA fits in is in the conservation planning space. And then my colleague Ben Dare has been leading the Arch Cape working group and has leveraged funding resources for the acquisition from Forest Legacy Funds for phase 1 of the project. Okay, so I guess quickly, 40 seconds to wrap up the next steps. Keep these results for peer review in the future, and do a sensitivity analysis with the % of area harvested, and keep providing technical assistance as need basis to different communities on the coast. Thank you so much for giving me this opportunity to present.
All right, Srijita, thank you. That's a lot of information. With those two back to back, it's like my head is doing this, but really good question. I'd ask Kevin to come on back, and we do have about 8 minutes for questions, and I got some for both of you. So first one for Kevin from Josh Seeds, the great questioner. Increases in the size of peak flows from less than a year, 1 year, and 2 year storms would result in mobilizing more sediment already stored in the channel, correct? That could include sediment transport from hill slopes years earlier. So it's kind of the tie between increasing stream flow and sluicing out the channels. Yeah,
and that's going to be a depends answer. I think you're right that yes, if we have greater occurrence of peak flows, even those small events, it could mobilize more sediment. Where the depends come in and where it becomes complicated is that I have colleagues who've done flume experiments on this sort of thing, and what they've illustrated with those experiments is that a lot of that sediment that was previously mobilized carries with it a lot of nutrients like phosphorus, and that phosphorus can stimulate some production of biofilms, and those production of biofilms then kind of holds a lot of that sediment together on the stream bed. And it's very fine and microscopic and not easy for us to see, but when through experimentation, what they've illustrated with that then is because of those biofilms holding things together, you need more shear stress, you need more energy, actually higher peak flows to mobilize that material, get it entrained and move it downstream. The flip of that is once you exceed the shear stress and mobilize that material, because of the biofilms, it can actually pull up sort of neighboring grains and mobilize more. So hopefully that answers Josh's question. Again, nature's not simple.
That's good, because neither is Josh. So that's a great answer for him. True. I'm glad that's not the answer for my question. So the next question is for Srijita. You demonstrated really good on the coast how the model would work. So especially with clear-cut harvest, how about in Southern Oregon or East Side and in drier forest types where more partial cutting is doing?
Yeah, that's a great question. So it would depend on how you calibrate the model. The model that I've been using is calibrated on the forest type, which is on the wetter side of the Cascades, and it's dependent on rain dominant systems. But when you go to the drier sites of either Eastern Oregon or other places in Oregon, you need to recalibrate the model based on snow impacts and how snow melt and snow accumulation would change with the timing of the flow. So that's an interesting topic, and I would probably rely on some results done by Bob McKen and his team on the drier side of forest.
All right, good answer. So another one for Srijita. You talked about changing harvest time with the rotation age, longer rotation, better. You also talked about the percent of the watershed that is being impacted at once. I know if I'm a landowner and I'm dependent on revenue from the timber harvest, it's really hard to say to lengthen the rotation age. I mean, if I'm set for 50 and you want me to go to 80, that means I'm not going to cut any trees for 30 years. So that probably isn't going to be a starter in some situations, but changing where the harvest is could be. So I know when I was back in school, we talked about you never want to have more than 25% because of short-term high flows. How about for low flows? Is it the same for thinking of the percent of a watershed that could be in any age class?
Yeah, again, a great question. So what I've seen in Arch Cape is the model is sensitive to where the harvest is located and how much of the harvest parcel is harvested in a short period of time. So definitely for summer low flows, it is somewhere between 20 to 25% before the response kind of kicks in to show.
All right, so that's good. So that still holds true. That's interesting that the number for the low flow and the high flow, the percent's about the same. So as foresters, we like those kind of rules of thumb. We can understand those. So going to the hardest question I've seen up here, Kevin, I always like to give you the hardest one. So you talked about the wildfire impact on water quality and water quantity, and we've talked about timber harvest impact on water quantity and water quality. Well, how about the dynamic duo? How about if we do salvage after fire? What does that add to the mix?
Yeah. Folks are going to be dissatisfied again with this. You know, there's no simple answer. And I've actually participated so I'm not even just looking at all of the other research out there, but I've been part of research on post-fire salvage logging where we have quantified that salvage logging on top of wildfire has increased flows, increased sediment erosion and mobilization, and increased delivery of nutrients like nitrogen and phosphorus to systems well beyond wildfire for multiple decades. It's made things worse. I've also participated in research that showed, hey, that salvage logging actually was sped recovery. Well, it creates a short-term bump up over fire. The systems recover far more rapidly. And then the third type of study I've been part of is actually have observed, and this was just recently in a study in California, and we're all put on our heels and shocked by this, and it corroborates a similar study that was done just before. If done in a certain way, what we found was the salvage logging actually reduced erosion and sediment delivery to streams. And there's nuances in all of that, and you need to look at the specifics of them. But I think if our operators are careful and they think about that and they look at that research, there are ways that it can be beneficial. I think where we're at, though, You know, I struggle with the harvesting work here, that there's just not enough pieces and not enough locations to have definitive outcomes. Wildfire and post-fire salvage logging is 10 times worse. The literature is thin. And so I think, again, we need to take this opportunity that we have in front of us to collect some of this data, because these types of fire seasons are going to continue to happen, and we need to be prepared.
A good answer. From my quick estimate, I think we're looking at about a couple 100,000 acres of salvage logging that's going to happen. So if there ever was a time to look at salvage logging, this could be the year to do it. Well, that's all we have time for. I did want to point out to Shrigita that in the comments, Art Todd from the Medford Water left his email. He'd like to have a discussion with you. So follow up with him. Thank you both. Excellent.
Sure. Thank
and this is a good segue to the breakouts, because of course we have breakout questions about what we've heard today. So you all have been assigned to breakout groups. And again, we have 12 to 15 people in each group, or possibly less, 10 different groups. As Shannon hits the button, you'll be asked to join. When you join, you'll need to unmute and also turn on your video. And after the breakouts this time, we're going to come right back here at 11:50 to do a report out. So no break after this. You've already had your break for the day. So enjoy the breakouts and take it away, Shannon.